Yeah, as you guys know, I've advertised this uh, several weeks ago already. Um, if you have been reading the news, like in recent months, if you have downloaded some of the talks or seen, what's the lineup at the recent NVIDIA GTC, you would have realized that there is a Singaporean company that is getting more and more in the limelight. So this company is actually dConstruct, as you know. Yeah, and we are very delighted to have Mr. Chong Jiayi, who is the CTO of dConstruct, to come and share with us some of the things that he is passionate about. And basically, I think it is a very good opportunity for all of the students here to hear, what his experiences are, and also very, it's quite a coincidence, lah. Which is also why I wanted to set this up. That your project, is like somewhat, or very much related to, some a starting point in trying to do some robotic development, which is what Jiayi is also very deeply involved in recently. Yeah, so a brief introduction, which I've also sent out just to reiterate, is that Jiayi has been in the industry being generally software engineering for a long time now. He did both his bachelor's and master's at Stanford, computer science, obviously. And he has worked at a number of very prominent names, including Pixar, DeepMotion. Recently, when I think he came back to Singapore, worked at GovTech as well. And now he's running his own company, dConstruct. So without further ado, I think I will let Jiayi do the rest of the introductions. Yeah, so Jiayi, you can take over from here. Oh, by the way, sorry.
Yeah.
By the way, Jiayi has mentioned that his video is not connected, so that is why we don't see him. But I have sent out the LinkedIn if you're wondering what it looks like. I mean, you can just Google his name.
I think the photo is not that important. Anyway. I think the content of the presentation is more important. So.
Yes. All right.
Okay. Thank you, Chuck. Thank you so much for the very kind introductions, and thank you for inviting me over to give a talk today. Very much appreciated. So today I'm going to be talking about what is dConstruct, and in general, it's more than just dConstruct. It's our experiences in deploying production-grade robotics in Singapore over these past few months, and what the real-world experiences are in terms of software development and what it means to build a high-performance, scalable, robust software control system, autonomous system for autonomous robotics. So I hope it will be quite interesting. So I'm going to be talking about some stories, some advice on deploying both legged and wheel robots in the real world. I'll cover quite a few of the deployment issues, the workflow, the tool chain that we use. Now, obviously, I'm not able to disclose too much if it actually reveals our core IP. So I'm just going to say, for the parts that I'm not able to say, I'll say you have to get the engineering right, which is a sort of a euphemism for saying I can't reveal the core IP. It's something that Andre Karpathy also uses the same phrase when he gives the his Tesla investor autopilot talk. So okay, so who are we? We are dConstruct Technologies. We're a very tiny startup, just 9 people, and basically we're building a self-driving stack for robotics. So like self-driving cars, but for robots. And we are focused primarily on outdoors, large-scale autonomy. So we're talking about autonomy in really very challenging environments. So not just outdoor, but indoors, but very large-scale kind of environments. So unstructured terrain. There's people, there's obstacles, different lighting conditions, long distances. So we're talking about some really challenging problems here, and we're targeting. Currently, right now, smart construction, building inspection, facilities management, surveillance, and security. So a bit about myself. I spent 20 years in the Bay Area. I got my undergraduate and master's degree at Stanford in computer science. My specialization is computer graphics, vision, and machine learning. I actually don't like the word AI. AI doesn't mean anything, so I say machine learning. Anyway, I was 10 years at Pixar as R&D technical director. I worked on a couple of films you might have watched. I have 4 US patents, gave a couple of talks at SIGGRAPH for dynamics, constraint simulation, physics solvers, that sort of thing. I spent 3 years at DeepMotion, where we're primarily using deep reinforcement learning to train sort of digital characters, humanoid characters, to learn physics-based motion using DeepRL, and so that to sort of address the issues of motion capture. All right, so the team is comprised of 3 robotics engineers with some, I think, really deep real-world experience. One guy with a Chinese AI startup, robotics startup, another guy from Airbus. We have a core ML engineer is actually from the Facebook deep learning group in Seattle, and then the other person is from ETH. A graphics engineer from probably from EA. Actually wrote the core Need for Speed game engine, graphics engine, and also Autodesk. And then we have obviously our web engineering team and DevOps team as well. Over 2 years running the Boston Dynamics Spot robot. So we're a very young startup, just started in March 2021, but I think we have quite a bit of experience. So what am I going? What do we do? What am I going to talk about? So here's a quick preview of what we do. This was recently in the news. We ran there was a 5G sort of event or trial at Sentosa, and we were one of the robotics companies participating. And we actually, I'll speak more about this later, but basically we went in there, deployed our production robotic stack, running both a legged robot and a wheeled robot that you can see here. And then we scanned not just this car park is actually for the media event. So this is just the media event, but we actually scanned the actual construction site with Gammon Construction, which is going to be one of our partners moving forward in 2022 for large-scale autonomous construction scanning with robotics. All right, so as I said, that's what we do. There's a huge why are we doing this, right? Because there's a huge opportunity for remote autonomous robotics in the real world. What I mean by that in the real world is outdoors, very difficult, unstructured terrain, unseen environments, different lighting conditions. Just it's not an easy problem. That's why we're doing this. We're trying to solve this problem because I think there's a lot of opportunity, and because it's difficult, it's hard, and we are interested in solving very hard problems. And there's a lot of applications, beyond just moving a robot, like a small vacuum robot in your room. We're talking about the real world where things really, really are unpredictable. So there's lots of applications in construction, building management, et cetera, especially relevant in the post-COVID world with manpower shortages. Okay, so let me just talk about our robotic stack, what the components are. We have a whole bunch of different components. I'll go through them in a bit, but basically we have a way to reconstruct a 3D map using our own custom STEM algorithms, using a hybrid hardware software solution called DashPack. And then we have our autonomous system and also our teleoperation system. And of course, we have our fleet management system. Our stack actually runs very robustly under 4G, even though the trial at Sentosa was run on 5G, but we don't actually need 5G at all. So we can run very, very robustly on 4G, as you see in a moment. And we have a hardware agnostic robotic stack called the Robot Hell, or a hardware abstraction layer, a bit like the Microsoft DirectX abstraction layer, where it abstracts out all the different kinds of GPUs. That actually allows us to run our autonomous stack on almost any robot, as long as we expose a very thin driver layer. So what we do is we offer a full autonomous robot end-to-end solution for everything: teleoperations, a heavily machine learning, computer vision influenced, what we call auto drive, pilot drive system, a very powerful missions waypoint autonomy system, 3D command and control, of course, and fleet management. So we do the whole stack, the full stack. I want to emphasize we're not doing rocket science here, so we're not trying to solve the DARPA challenge or publish the next hot ICRA paper. So we have to make it work in the real world for our customers. So a lot of this is not magic; it's just a lot of hard work. All right, so the first one of the before you actually start doing any kind of autonomous robotics, the first thing you need to do is actually generate a 3D navigational map for your robots. In the real world, we do 3D, not 2D. 2D is not sufficient for outdoor or even indoor complex navigation. It's only good enough for like an office environment, a simple one. But in the real world, you're going to need a 3D, somewhat accurate 3D point cloud map. And so we have this process is actually very time consuming for a lot of companies or academic institutions. Some people take like even up to 2 or 3 days if you want to map out entire environment that's about 1 or 2 kilometers or 5 kilometers long. So we have a solution called DashPack, and it's essentially this man-portable pack you see on screen, and you just walk around casually. You don't even have to worry about vibrations or anything. So what happens is our core algorithms will sense, compensate for all motion, vibration, etc., and then collect all the point cloud data as you walk around. And then as you can see this, so let me pause the video. So that was, let me just play it again. This is actually Punggol Digital District, which is where SIT will be located, right, in 2025. We got invited to the PDD event, and we mapped out the entire area, not just the tent. This is part of it. And so once it's done, we can map it on record time. You dump it into our 3D application called Dash Explorer, and we can actually reconstruct the 3D map using our own highly optimized custom SLAM algorithms in what we call faster than real time. So we can actually, if you say, let's say you took 6 minutes and 30 seconds to map, you can actually reconstruct the entire map here in 1 minute and 37 seconds. That's what I mean by faster than real time. And so this actually allows us to basically create a map for, say, regular traditional robot waypoint autonomy in record time. So we were there at PDD and we mapped in the morning, and within, I think, 15 minutes, we actually had our robot running immediately. Within 15 minutes, we had a robot running immediately. It was off and running, on the ground with no issues. So what happens is this map gets uploaded to our backend cloud system, which gets pushed to our entire fleet of robots, and then we can then run it with no issues. This system allows us to iterate really quickly. We can deploy production grade robotics in record time, which is, in my opinion, a very important part of the deployment process. So we do a lot of sensor fusion. We fuse obviously the LiDAR, the camera, and IMU, and then it's our own custom algorithm that actually allows us to do all of this stuff. It's heavily optimized C++ code, highly parallelized with either OpenMP or TBB. We obviously employ a lot of CUDA GPU optimizations as well. The 3D point cloud discovery tool is called Dash Discovery. It does a lot of very fancy things as well. It also has our own custom auto alignment point cloud and retrieval algorithms, more than just regular ICP. You actually generate a whole postgraph for that one. The point cloud itself, we can actually generate a mesh through a sign distance function and then run marching cubes through it to generate a renderable mesh. That's for preview. The cool thing about this is because we are all running native C++ code, the on-device backpack device is an extremely low-powered Jetson Nano. This is what happens when you can actually write high-performance native code. You actually get to run on low-power embedded systems. And of course, the core algorithms run on the PC for reconstruction. And then the final point cloud, as I mentioned, actually gets pushed from our system all the way to our backend cloud system over the air. So this means that all robots running DashPack can get updated. It's like almost like a Tesla car, if you mentioned, right? You drive the car, and then we can update your maps over the air immediately, and all the robots in the fleet get the new map, and they're off to the races to do navigation on a new environment. Okay, so once you have the map, the next thing you need to do is you want to start your actual autonomy, right? We have different kinds of autonomy, autonomous frameworks in our system. The most obvious one, which the basic one, but also not difficult, not easy to implement, is the 3D waypoint autonomy system. The difference between this and a regular 3D waypoint autonomy system is, as I said, this is 3D, not 2D. It is built, engineered for large-scale environments, unstructured environments. So a lot of work and engineering work was done to make sure that it actually scales and runs properly and is robust. It can also deal with a fair amount of changes to the environment. So even if your map changes, obviously if there's drastic change, there's no way we can fix, we had to rerun Dashpack, but Dashpack's really quick. But for I wouldn't even say minor, for somewhat medium level type changes, it actually responds quite well. We do a lot of stuff, not just regular DWA, we do MPC and a couple other tricks of that I cannot mention. It is integrated into our 3D command and control system, which we are constantly improving. This is actually the old UI, but we demonstrated this actually at the DHL Logistics Supply Chain Summit in 2021, where we ran this full system over 4G. Almost like a last mile delivery scenario. So it traversed, as you can see, very challenging type of terrain. So staircases, the floor, outdoors, indoors, lighting conditions, roads, etc., etc. Also walked around people, and then it was completely controlled remotely. So we were sitting in the Capital Land office, and then the robot was about, I think, 5 or 6 kilometers away. So that was a real test of how scalable the system is. The other cool thing about this system is it's more than just a regular waypoint system. So this is what we call a programmable missions framework. What it means is that we actually have our own custom scripting language that you can actually script specific commands for the robot. Say, go to this waypoint, do something. Go to that waypoint, run the scanner. Go to that waypoint, take a photo. Go to this waypoint, run a hazmat detection center, whatever, right? So everything is customizable. That code gets sent into over there, 4G, 5G, or Wi-Fi through to our robot stack, and then gets JIT compiled into native code. So it's very fast running on the embedded system. What this allows you to do is you can have a very customizable and programmable missions framework, which can do a lot of things. And that actually allows us, our entire robot stack, to be very flexible. That's how we actually can integrate all these different payloads: laser scanners, 360-degree panoramic cameras, temperature sensors, the works. And it's something that we're very proud of, and it's something that we run all the time. Okay, so you saw the waypoint autonomy system, but sometimes what if you just wanted to manually pilot the robot, right? Sometimes there's no substitute for manual piloting for whatever reason. So of course we have a real-time remote teleoperations or beyond visual line of sight, depending on whether you're in a robot mode or drone mode system. Very simple to use. You just use a joystick. And again, fully remote. So you can pilot, just like the previous system, you can pilot this anywhere. We've actually tried the system from here at Chengdu, so that's how robust the system is. We can actually do up to 20 frames per second video streaming at 720p, just over 4G. Of course, with 5G, we can do up to 4K, close to 4K, I'll say. But even with 4G, we can do low latency, high performance video streaming. And of course, all the controls are, of course, also low latency, high performance. And everything, as you can see, can stream multiple cameras as well. And everything is, everything that goes through our streaming stack is secure end-to-end. So everything is encrypted. It's all meant to be secure and scalable and high performance and stable, et cetera, et cetera. So this is also a key part of our system, but it's cool. But the next one is even more interesting. So once you have teleoperations, the next thing you want to do is, what if you could actually have a hands-free, basically a self-driving experience, right? Basically have teleoperations, but hands-free. So no person at the wheel, sort of. And we have that. So this is our really part of our core IP. This is our what we call Auto Drive. It is heavily inspired by a paper from David Su from NUS that we work closely with, but heavily modified, just inspired. We do a lot more things, actually, multitask learning and a bunch of other tricks to actually make it production ready. So, but I'll say heavily inspired. This was presented at NVIDIA's GTC 2021. I'll show you the real video. So this, what's cool about Auto Drive is in the waypoint autonomy system, you actually needed a map. The Auto Drive system is done in such a way that it is mapless. So we're running this is actually a science center. This robot has never seen this environment before. It's completely unseen. So no maps, no LiDAR, no GPS, no radar, just pure computer vision alone. And of course, a lot of deep learning, a lot of tricks in computer vision, and of course a lot of C++ code and a lot of engineering work that allows us to do this sort of thing. So this system allows you to have a hands-free, basically a self-driving autopilot, we call it auto drive experience, where you just sort of let it run, and then the system just decides how to follow the roads. But it's not just road following. We actually have a checkbox where you can say enable grass, and it'll actually know that it can walk on grass. And then you sort of give it high-level intentions. It's like telling a Grab driver where to drive. So when you come to a junction, you can say make a left, and the system will be smart enough to decide when to make a left safely. Or if it's not safe to make a left, it won't make a left. It's also smart because it does what we call scene understanding. It has a holistic view of the entire world. So it's not just regular lane following. If there's actually obstacles and people walking in the scene, it will actually make an intelligent decision whether to slow down or to weave in around the people or whatnot. So it does a lot of intelligent things. It's also able to cope with drastic changes in lighting conditions. Let me just replay that again. You can see in this level, this is actually SIT, by the way, also completely unseen environment. In this level, there's shadows, there's things obstructing it. And also I want to emphasize again, it has never seen this environment before. And it's able to make intelligent policy decisions, formulate right driving policy to get the robot, across this park environment. So anyway, so we're getting a patent for this. This is part of our core IP. NVIDIA was impressed enough with what we showed them that they actually invited us to the GTC 2021 conference to give a talk about this. And we also an NVIDIA Inception partner, startup partner in Singapore. But yeah, so we're very proud of the system. And this system, we're actually installing on all robots right now to deploy them in outdoor environments. Yeah. Okay. Now, when you have all that cool stuff for autonomy, you still cannot ignore the backend system. So of course, we have a fleet management system. It's called Dashboard. It does a lot of things actually. Maybe not as exciting as the Dash Pack or the Auto Drive or autonomy system, but it's still actually the key part of our system. It is a cloud-based, full-on cloud-based fleet management system. It does a lot of things. One of them is robot device and discovery. So when you turn on the robot, it runs our stack. Robots automatically broadcast themselves, advertise themselves to our backend system, and then we can discover all your robots, and then you can then log in through secure authentication, of course, and then encryption. And you can also monitor everything that a robot does. You can see the CPU uptime, the memory, the temperature is really high, as you can see, although we're improving the cooling system. The speed, you can also see where it's moving in a 2D environment. This is just for monitoring, but for actual controls, right? For actual controls, you're still going to need the 3D command and control system, which is our own custom 3D engine for that sort of thing. But this is a very powerful system as well that we also deploy at Sentosa. And this system also allows us to take what the robot has and then broadcast it as an RTSP stream, which is what we did at Sentosa. And so Gammon Hong Kong was actually tapping into the RTSP stream to run their own video analytics solution for safety PPE and other kinds of video analytics applications from Hong Kong to Singapore. So it's a very key part of our system. Okay, so let's talk about the technical details. So what's our tool chain? We are a C++ shop. I love C++, probably my favorite language. And if it was my choice, there will only be one language, which is C++. Modern C++ 14 and 17, which is great because you get all the niceties of a modern language, right? Also, if you stick to modern C++, you get to the safety guarantees of all the, previously all the bad things about C and C++ are mostly gone if you know what you're doing. So you get smart pointers, atomics, move semantics. Move semantics, very powerful concept, which I think is a big deal for performance and also makes your code safe if you know what you're doing. Again, C++ also has a concept of zero cost abstraction. You only pay for what you want. So that actually allows, when you're doing like actual high performance code that needs to be scalable and needs to run robustly 24/7, this is a very important thing to have. We, of course, employ CUDA for our GPU applications using GPU compute, and we use Thrust, which is C++ framework around raw CUDA. You can also use raw CUDA, but Thrust actually has a lot of advantages because a lot of the parallel compute concepts and algorithms like MapReduce, accumulate, maybe like generating a uniform distribution of random numbers are also within thrust. So you don't have to reinvent the wheel, and they're highly optimized for NVIDIA, but you can still, write raw CUDA code if you want. So there's no stopping you from doing that. Some of our robots unfortunately use Python. Python is really not my favorite language, but it is a beginner language, right? It's a very accessible language, which is fine. So what we do is we have a very thin Python abstraction layer running on top of high performance C++ code. And then we basically expose, wrap our C++ code into Python classes, and actually done a bit of magic where you can actually even have Python classes inherit from C++ code and even override the virtual methods. And then it will actually still go back, invoke back into the C++ layer. So what's really cool about this is now that we implemented this, we can do all multi-threading in C++, because as you know, in Python, multi-threading is extremely problematic. In fact, it's terrible for performance. And sometimes multi-threaded code in Python runs slower than single-threaded code, which is extremely sad. This is due to the fact of the core Python implementation, something to do with what you call the GIL, or the global interpreter lock. So you can read that up, but it is a huge limitation of Python, unfortunately. But Python is useful for many things, right? I'm not saying it's just not good for performance, right? So, but there's ways to sidestep it, and the way we've implemented it is I think sort of best of both worlds. So our end users, people using our SDK, if they don't know C++, they only know Python, they can still tap into our SDK, but they get all the performance benefits of our API. So we don't do any real compute in Python, it's all done in C++, and that allows us to have high performance, low latency, but we can still expose some easy stuff to beginners in Python. We don't use ROS. ROS is great. Unfortunately, ROS is not great for performance. ROS is great for research, and I think to really get up to speed and get stuff running. ROS is great. I'm nothing against ROS, right? But it's not really good for production grade robotics. Even ROS 2, in my opinion, has some issues. It's a big improvement on ROS 1, but ROS at the core is an RPC framework. And so if you given a choice, right? The problem with that is, you're still going to have to sort of invoke. Let's say you have a LiDAR system, and then you have your own core, I don't know, localization nodes somewhere else. To get both of them to talk to each other, the process of retrieving the LiDAR point clouds involves you actually having to serialize a packet, right? So there's the cost of serialization. You have to send it over the wire, then that part is unserialized, unpacked, right? So that's a lot of memory copies. There's a lot of heap allocations, and then you have to go through the networking stack, which is not ideal. Even if it's switch to the IPC, it's still not ideal. What you want is a direct function call straight into the LiDAR layer, LiDAR API or SDK, whatever that's exposed to you, right? You want to read straight from the port. So ROS is, as I said, it's a great system. I have nothing against it. But if you are building a production grade robotic system, if you know what you're doing, you probably should build your own. There's better options out there. And the way we have achieved it with the performance that we expect if we don't use ROS. And also security is a problem. Now ROS 2 does have security, I know this. But again, if you know what you're doing, you can probably do something better. Boston Dynamics themselves also do not use ROS. When they came to talk to us, we talked to them almost like every other 2 weeks. They too feel that ROS, a good system as it is very limiting for production grade robotics, because it's just not ideal for performance, security, scalability, and deployment, that sort of thing. We have one custom serialization framework just using protobufs, but you have lots of options, right? You can use Cap and Proto, you can use buffers, there's a lot of options. Again, ROS's serialization framework, even in ROS 2, the ROS 2 version, which is based off DDS, it's okay, but it's 2021 now. There's a lot of other options, which I think are not only just as good, but maybe even better, also more lightweight. So yeah, that's basically what it is. So I'm going to show you some results. Certus actually is one of our customers as well, but I'm not allowed to show it because security reasons. So I'm going to show you other stuff. I think I showed the DHL supply chain. Let me jump to it again. Hang on a second. Yes. So this is the DHL supply chain logistics 2021 summit. It was like the first deployment of our system, I was very nervous, very challenging. And the first deployment was this sort of very challenging terrain. So staircases, different lighting conditions, semi-urban to outdoor environment. And they really wanted it to work. So we went there. This is the first iteration of our autonomy engine, the 3D system that you can see. We obviously dash packed this is a big chunk of Science Park actually, and it ran extremely well, fully autonomously. We're sitting about 6 kilometers away from the actual deployment site where the robot ran. So that was, I think, pretty cool. And then, of course, the system running, next iteration of system, this is at the Sentosa, the Gammon construction site, where it was actually doing real work. And then also broadcasting the video as an RTSP stream to Hong Kong, to the Hong Kong office. So this one got the interest of a lot of people. I think Gammon was very excited when we managed to pull this off. So we actually managed to get this thing done, and they're very happy. That's why next year we're moving forward with them for autonomous robot construction scanning. Now this is done through 5G because it's the part of the Singtel 5G trials. But just to be honest, we actually ran this this actual video. This actual scanning, Singtel's 5G was not working that day. So this was actually done through 4G, and it ran just as well. In fact, we were streaming the same RTSP stream to Hong Kong with no issue. So just to give you an idea that our system is just as robust over 4G and 5G or Wi-Fi. We've optimized the entire streaming stack by a lot to make it work. So we don't need 5G, although 5G is great. You know, you get probably even much better video, but we can function on 4G just fine with this sort of performance. Yeah. Of course, we also, to show you what the results are, like when we do autonomous 3D reconstruction, what can we do? Let me show you. So this is an example of the quality you can expect from the construction scanning. So here's our system running a wheeled robot instead of Spot this time, a change. This is our scanning the Sime Darby car park, which is our office car park. And you can see on the left is our new improved 3D command control system. You can control multiple robots, of course. You can see a live video feed. You can also BV loss, teleops, everything. You can do the whole thing from that command control panel. This is just through 4G. And you can see the robots moving and stopping and then scanning, running the BLK360, which is the high resolution Leica scanner. This has an accuracy of within, I believe, 3 to 5 millimeters. So this is the quality of the scan you can see. It's not even cleaned up. This is just straight from it. And what's cool about our system is that you can do multiple scans. The BLK360 itself, let me pause it. The BLK360 itself doesn't actually have localization. So if you were to use it by itself, you would actually have to, other than manually moving the scanner around, after it's all scanned, you have to manually shift and align all the point clouds yourself manually. And if you're going to be scanning hundreds of scans, you can see how it won't scale. You're going to be wasting a lot of time. So what our system allows you to do is, let me just step back. What our system allows you to do is, we've done sensor fusion. So we have actually tapped into the BLK360 and fused the point clouds with our robot autonomy stack. So essentially, we are telling each scan where they are. And more than that, it's more than just a simple fuse. We have our own auto alignment, auto stitching, and post-graph algorithms that actually will give you very high quality auto-aligned stitched 3D environmental point clouds end to end. So you just, once it's done, you load it into a dash discovery from the robot, and then everything is done for you automatically aligned, automatically stitched, the works. And this is, of course, done with our own custom core SLAM algorithms and our compute framework, which allows us to do it. Even Leica doesn't have this capability. So we showed it to them, they were very impressed, which is why they're also going to be working with us very closely. Just to show you more results, this is also from scanning another part of the office. You can see how the system's building up, right? The 3D scans, and then retrieved from a robot. And then you can see how it's actually initially not aligned properly. And our core compute algorithms actually start to automatically refine and optimize and adjust. You can see how everything snaps back together. It's very accurate, right? So once it's done, you have sort of a digital twin that you can use that's autonomously scanned by the robot. So yeah, that's what we have. Okay, So yeah, I think that ends my presentation. We are actually looking for interns at the moment, not full-time, but interns for website video editing, technical documentation writers. Definitely looking for help in QA and unit testing. And then if you guys have any kind of hardware or robot deployment experience or mechatronics, we're also very interested in that. So yeah, thank you for coming to the talk. And I think I'm done with the presentation. Thank you.
Okay, thanks, Jiayi. I think that was really interesting. Although I've heard it like a couple of times now.
I'm sorry.
No worries, no worries.
Sorry,
but
sorry.
It is still as fascinating that how you guys have pulled it off using just 9 people. You were saying.
Yes.
Yeah. So
since March.
Yeah, and I think that this format is a bit more structured. So I saw that all the different components, dash pack, dash. I like how innovative you guys are with the names. Autonomy, I think. Dash autonomy, dashboard, even. Okay.
Yeah.
So,
it's just naming. It's just naming.
That's good. Yeah. So I think that allows us to really appreciate the kind of complexity and just the sheer amount of different things that you guys have to put together to make everything work together. So I think that is a good starting point for our chat now. So because as I mentioned to you that I actually made I'm going to make the students write a reflection. So
sure.
Yeah, I think I'm sort of needing to ask you a few questions about how you did it. So you described basically what you do, which gives us a very good appreciation of the complexity. So I think we are really curious, how you guys actually pull this off. So maybe to start off, I think the first question for software engineering students is definitely how what sort of a development process model even if you guys actually have stick to a certain model, whether it is a traditional related to traditional waterfall or Scrum or something altogether different altogether. Just wondering whether you could speak a bit about that.
Sure. To be honest, we are I wouldn't say disorganized, but I think in such a way that we because it's a very small startup, right? So we don't need to be too formal about the processes. However, we do have like there's no daily stand-up, but I make it very we just have a daily update, and then we of course use Jira to post the features and all that. We also have a bug list, of course. But in terms of the process, essentially this is like more like traditional software shop. I'm not like as cool as hip as the young people these days. So it's more of a traditional software engineering shop. As I said, we're all C++ people. So for code, build management, we have a build engineer, and it's all done through CMake, of course. In terms of making the code manageable for dependencies, we manage it through VC package, which is surprise, 2021. There's actually package managers of C++ now. There's like Conan, that's VC package, and I think there's one more I forgot, but there's a bunch of them. So we do have a proper so to make everything organized. I guess that's your question from a software sort of I don't know, management standpoint. We use dependency code package managers as far as we can. And then, but for certain packages like say Open3D or whatever, if the whatever's in the dependency manager sucks or is outdated, we build our own, but we make sure that it is still properly built. There's like a standard workflow to it, right? And and then all the projects can build and then can find the correct dependencies. Then we of course we have a nightly build of course, just in case anything breaks. For a couple of our products that we're pushing out for more very soon. Although to be honest, for robotics, it's a bit difficult. It's actually a lot more. It's not pure software. You know what I'm saying? So there's only so much you can do for this sort of unit tests and all that. There's no substitute for testing in the real world, unfortunately, and that's the reality. It's a very difficult problem. I don't think people have figured it out yet. So, but that's the reality of it in 2021. Yeah. So that's basically how it is. our code runs on cross-platform, of course. We target Windows and Linux. Sorry, no Mac. So yeah, sorry.
No,
yeah. But that means our code has to be, at least properly compliant with both platforms. And so we build, on the cloud, obviously, as you know, we also build from different architectures. Build for ARM, x86, right, x64. So on the cloud, we spin up different instances that we nightly build the different components for different platforms, and also the different architectures, just to make sure they all run properly. I guess I'm not sure if it's a good answer, but that's what we do.
No, I like how you structured answer in terms of the tools that you use, right? So on that, you mentioned like Jira, as well as CMake is like a build tool dependency manager. But just wondering whether there are other tools. You also mentioned like Jira, and you said like, of course. So does that mean that Jira, in your perspective, is like a good tool, or is like the industry standard?
I'm not sure if industry standard, but it works for us. I mean, I'll say that it works. I'll take anything that works. We are on Atlassian, if you want to know. So we have the full like
Confluence.
Yeah, exactly. Use Confluence, use Jira, of course, and then we do the pull requests through Atlassian, which is, I think, a very important component of proper software engineering. Obviously, different branches, and then people do pull requests, and then we have reviews from, obviously I review all the code, obviously other people as well. We at least have 3 to 4 people reviewing the code to make sure that proper software engineering standards are adhered to. Now, the other thing I think which is quite important is, especially when you're writing native code, C++, is we run our code quite frequently through static analysis. So in a lot of modern compilers, modern C++ compilers have static analysis tools. You run it through that, you can catch a lot of the bugs, say some of the memory stumping bugs that you normally not find. We also do a lot of profiling, including performance guided profiling. So we run it through a profiler, and then we have to find out what's going on. So these are some of the standard processes that we do, right? So once the code gets checked into a separate branch, then we test it, and then we run it through static code analysis. We do some profiling, and then we do a pull request, and then we get people together to do like code reviews, make sure everything is fine. It gets merged back. Then we do more testing, and often things still break. Then we fix it again. So that's the sort of very iterative process. But I want to emphasize again, it's not easy. I mean, easier for a regular, say, doing a regular web app, right? It's easy. But for robotics, unfortunately, you can do all the testing you want. At the end of the day, you run a real robot, it's going to break. That's just the reality. It's just how it is, because it's a hardware thing. There's a lot of unexpected things that you don't expect. For example, temperature. Your code might run very well on a desktop. You put on a robot, after 10 minutes overheats. Your Jira, your pull requests, your static code analysis, none of that would have caught it, right? Even your testing on your desktop. So some of these things you just have to be aware of.
I see. Yeah. I think your point about testing in terms of versus software versus hardware, which your projects are heavily dependent on both aspects, I guess, is very interesting. But I think we'll come back to testing a bit later if we have time.
Sure,
by the way, you have to leave at 11.
Yeah.
At the latest, right? Yeah.
11. Yeah, I'm fine.
But I think we should be able to finish.
Okay. Okay.
Way before that. So back to the question about in general, how you manage development using tools, right? You actually answered half of my question that I was going to ask, which is code review.
Sure.
So pull request, code review. Just wondering what if you are able to review what you not exactly, but what you roughly do in terms of reviewing other people's code. Do we actually pull and run, or you are reading the code and?
A very good question. So we obviously, the first thing we do is we check out your branch. Then we try to build it. Sometimes it's not even built, and it's very embarrassing, right?
Yeah, I mean,
it happens.
It's good to know. Yeah. We are not alone.
Sometimes people put a code review, and then you without even reading the code, you check out the branch, and then it just doesn't even compile. It's very sad day. Never make sure that never happens. Anyway, so after you build, we try to run it, and yeah, sometimes it, unexpected things happen. We run it. We also deploy on the robot actually. So we run that separate branch on a robot, Spot or the wheel robot, whatever. And then we try to run it, and we catch a lot of problems then. It's only after all the problems have been caught, then we go back. Obviously, we fix some of the code first, but after the code is sort of fixed, we go back, we verify it's properly running, then we start looking at the code again for real, and then we start seeing how it was actually written. So oftentimes, a lot of things can be not just optimized, but refactored for just cleaner code. So the general philosophy is, if you're writing a lot of code, right, then you have a problem. So the best code is, as little as possible. Like your train of thought should be very clear. So your function should never be too long. If you have a function with a lot of lines of code, that's always a bad sign. So please don't do that. You should always break up your functions into much smaller modules if you can, because that allows you to have a cleaner thought process, and also allows you to reuse sub-portions of your functions for other pieces of code. So that's something that I stress a lot about, and I think people care about as well. Also things that are important, like we try to not make pass like variables by value. We want to, as much as possible, pass things by reference. Now, of course, I know not many languages like Python or C# or Golang or JavaScript pass things by reference by default. But in C++, you have a choice of passing by value or by reference. And there's reasons why you want to sometimes pass by value, but oftentimes you mostly want to pass by const reference, not just reference, but const reference, so the compiler can make further optimization. So these are some of the things that we look for. Of course, also making sure you adhere to standard like object-oriented guidelines, right? Your code is properly written. You can, if it can be made into a class, sometimes, then sure, go ahead and do it. And yeah, sorry, go ahead. What were you saying?
All right, I just trying to delve a bit further, because you mentioned a couple of things which are some of which are higher level in terms of trying to detect whether they are modularized or could reduce no repetition, and then there's some of the things that are very specific, like seeing whether they are passing by reference or value. So is there a way that you are doing this, or reading? Is it purely by reading the code?
Exactly. So after we've verified everything, so we don't have an automated tool. I guess that's what you're asking. Unfortunately, we're kind of primitive, so we actually read through the code. And my experience, actually, even when I was at Pixar, is there were some automated procedures, but nothing. You just need a really good experienced software engineer. That's normally the lead or the supervisor to still go through the code again just to make sure everything works.
Is that person you?
Pixar, yes, it was me.
Okay, what about I guess dConstruct?
So dConstruct is still me. Motion, it was me as well. I was always a technical director, so it was always my job. Yeah, so I've been doing this for years. It's always my job, so I know what I'm doing. Yeah, I've been doing this forever. So yeah.
I see.
So
cool.
yeah, but we have to make sure that these things are properly, like the proper, and also of course so there's checks for proper refactoring, right? So functions not too long. Make sure you obey the object-oriented principles, or if you don't like object-oriented stuff, you like the new school. What's that thing? You probably know, right? Less inheritance, but you sort of, what's that term again? I'm very bad with terminology. You have classes, but you add features to it.
Delegation over inheritance.
Yeah.
Composition over
inheritance. Yeah. I'm fine with either. Check, as long as you know what I'm saying. I'm fine with either, but just make sure if you want to go for either, go ahead, but do it the proper way. You know what I'm saying? Basically, it has to be clean and reusable. So that's that sort of thing that we check for. Then we check for language specific stuff, right? Like by reference, by value. Can you use move semantics here? Are you using smart pointers correctly? Like in the cases where you can use unique pointers, so instead of shared pointers, you use unique. Do you understand all these things? Then we check for crucial things, dangerous things like race conditions. Those are important. Are you using atomics? Are you locking? Are your mutexes done properly, right? Is your code thread safe? That's very important. So we check for those as well. And then of course we check for the algorithmic things as well. So let's say your code is clean, but you're doing really dumb things. You're doing n square search. That's really dumb, right? You should obviously have a very good understanding of algorithms and data structures. So could you make it logarithmic, or could you make it like even order one if it's a lookup, right? So there's all these things that we check for. So obviously code, whether it's properly written, is it properly refactored, are using the right design patterns, and then language specifics, right? Specific to the language, like C++ stuff, or even Python. There's also Python specific things, right? For example, if you're using Python like in range, the range operator, depending on what you're using, it's either instantiating a full range thing or actually doing by a more optimized enumeration. So there's different things in Python that you be aware of as well. So anyway, so language specific stuff. Then we look at the algorithm specific stuff. So these are all the different steps that we take to ensure that your code is, I say passes the standard before you merge back to the master. But even then, I would be honest, you can do all these checks, you run a robot, still crashes. So I mean, this is a reality. Unfortunately, I mean, there's really you still have to test it. I mean, this is just a reality. Because hardware is a very tricky thing. Yeah, composition, exactly. That's the word I was looking for. Thank you for that's what composition. Yeah. So I'm talking about inheritance with composition. So if you prefer composition, it's fine too. I don't really care. But just make sure you stick to it and make sure that it works. Yeah. So those are the things we look out for.
I see. Yeah. So thanks, Percy, for
Thank you. Yeah, it's composition.
That is the word. And
I'm very bad at composition. Yeah. So
no worries.
Yeah. Exactly.
Okay, so I was just going to say, like, I see quite a number of questions in the chat, but sorry, I think I have several other questions that I'm really curious about. And I think I take back my estimation that we may finish earlier. You mentioned so many things that I think we can probably chat for a long time on all these aspects of how you do software engineering in general. But you mentioned branching and doing many different things before you merge to master. So that triggered something that I wanted to ask in terms of whether you guys have any branching workflow that you follow.
Well, workflow is basically if you think so if your change is going to cause touch the core code. Let's say it touches the localization code, or it touches the, I don't know, the part of the camera system vision code. You probably should branch, because we don't want to break what's in production, right? You don't want to break what's running at Sentosa. You don't want to break what's running at Gavin on the construction site. But if you're adding something new that doesn't really touch the rest of the dependencies, we're actually okay with you just directly coding in master, but it has to be really, really separate. Nothing is going to get broken, and you better make sure at the end of the day that you know what you're doing, and it hopefully won't break the nightly build. Yeah, but that's basically our philosophy. In general, we always branch because branches in Git are kind of cheap, right? So at least for Git, so we branch a lot, and then we test it, and then we do all the necessary checks and code reviews, and we merge back into master.
Yeah, and I guess to do that, you need to really hire people you trust a lot, right? In terms of just
we're very specific about hiring. So.
I see.
We're very specific.
That is why you can allow for sometimes somebody actually committing right to straight to master.
Yeah, but we try to discourage it, But but if you know what you're doing, then sure.
Cool. You also mentioned a lot about doing all this code management without mentioning of GitHub. So I'm just wondering whether you do use GitHub.
We use GitHub for if there's a useful open source repository that we want to use, so we use GitHub for that.
Okay.
So for example, there is a very good repository called RTTR. Yeah. That's a reflection. It's not, by the way, it's not. People always say C++ doesn't have reflection. That's not really true. There's a lot of reflection libraries out there that enable reflection in C++, and also I think in C++ 2022, there's going to be reflection. But anyway, there's a good very good reflection library called RTTR, which enables reflection in C++, modern C++, 14, 17 that we do use. So we for those those sorts of things we use GitHub. But obviously our repositories are private, so we use Bitbucket for that.
Bitbucket, okay.
Yeah, we don't use GitHub. So yeah, everything's behind a closed wall.
I see. But GitHub, you can also do it privately. So just wondering why choice.
Because upper management,
okay,
my boss decided that they had everything built in, right?
I thought you were the boss.
Oh, sorry, go ahead.
I thought you were the boss.
I am, but there's also like investors, the people providing the money. They because I mean it makes sense, right? So it's like you get Atlassian, you get the full package, right? You get the Jira, you get the Confluence, you get the. I mean, to be honest, I don't really care. I can use GitLab if as long as we have Git, it's fine. Yeah.
I agree.
Yeah, but for them, I think for them when they say it was a full package, they just
Cool. Yeah, because for the students, I think most of them for this introductory module, most of them just use GitHub. And
GitHub is great.
The management features there, but I must say Jira, it really takes that up.
But GitHub works too. I mean, there's nothing wrong. I think it doesn't matter what you use as long as it's Git. You have a proper code management tool. It's fine. It all works. It's all good.
Yeah, totally agree. Yeah. So maybe I ask a different type of questions with regards to software engineering, and then we will move to some of the questions that our students are asking.
Yeah.
So just now I was mentioning, you showing us this picture of many different components, and then you're going into each one of them, the autonomy, the dash pack, pilot, auto drive, and all these different things, which looks like really a lot of different stacks, and whether they have shared stacks. It just feels quite mind-blowing how everything is put together. Just wondering whether when you design this whole architecture of architectures, do you follow any or what do you use to manage the design of these things? I mean, in our module, we teach the traditional way of doing things, using knowing some of the famous patterns. I mean, MVC is probably not. I mean, it's a famous pattern, but not really applied across so many the deeper stacks across to your hardware. Probably more of the front end, and then having them structure different classes, grouping different classes into common modules, and then trying to do the interfaces between them. But I'm wondering whether you guys have a diagram or hierarchy of diagrams to help you talk through and visualize how everything fits together.
Actually, it's a good question. I think the design is I'm not sure like how much computer graphics experience you or anybody has in this presentation, but if you've dealt with any low-level graphics API, it's actually very similar to those. So you can take a look at the graphics stack, API stack of say Vulkan or DirectX or even OpenGL. The OpenGL is a bit more high level, but I think or even a 3D engine, say Unreal Engine or maybe Unity. It's quite similar. So this is what we call a high performance stack, which sort of interfaces with the hardware. So in case of a graphics stack, you're interfacing with a GPU, right? And game engine, you're interfacing with different backends: Vulkan, DirectX, OpenGL, Metal, but you're still talking kind of close to the metal, right? You're still sort of it's pretty close to the hardware. Ours is also very similar, even though it's robotics. So you have your you have different components, and these components were not done just for fun. They were actually after a very long thought out sort of like we knew exactly what we were building. These are all like crucial components that you require for actual production grade autonomous robotic system, and they're built in very similarly to, I would say, a graphics hardware stack actually. So you have, as I mentioned, I have something called the robot hell hardware abstraction layer. That is actually heavily inspired by Microsoft's DirectX hardware abstraction layer. It's got a registry system, component plugin system, everything. But instead of registering, in Microsoft's case, the HAL registers, it abstracts out part of a lot of the GPU hardware. So where you submit, points and indices to the GPU, you have like to the buffers, where you abstract out the GPU memory, the video memory, where you abstract out the compilation of the shaders. In our case, we're abstracting out the robots themselves, right? So you abstract, but they're really equivalent. For them, it's the GPU. For us, it's the robots. And so if you think of it, then it makes a lot of sense, because we're sort of both trying to do the same thing. They're trying to abstract out and operate a GPU. We're trying to abstract out and operate a bunch of robots. And so we have all these different components that fit into the overall architecture. So it's actually not that complicated once you think of it. You think of it in terms of what's required. Okay, so the equivalence is here. So in a graphics stack, you're gonna want, first of all, what you want to do, you want to be able instantiate points. You want to instantiate indices for topology. You want to render polygons. You want to be able to compile your shaders. Vertex pixel. Vertex fragment, geometry, tessellation shaders, whatever, right? And then you have your transformation stack. So they're all like layered. For ours, it's like, tele operations, and then on top of it, you layer the auto drive, right? And then a separate part, you have your autonomy, the full waypoint autonomy. Then you layer on top the missions framework, right? And both of them go up again and talk to the HAL, the robot HAL, which then goes up and talks to our cloud layer. So it's actually, there's a hierarchy. But these components are broken down in a very similar fashion to a low-level, high-performance, I'll say, hardware stack. That's basically what we're building. Yeah. So I'm not sure if that answers your question, but that's how it's organized.
Yeah, that certainly sheds a lot of light on how you have structured broadly, what the components are. But if more specifically, I think the students may be wondering what they have learned in terms of using things like UML diagrams, like component diagrams, drawing some socket and ball things to represent interfaces and stuff like that to help design the architecture. Sometimes first design architecture first and then write the code. Does that seem something that is it seems like something that you would find useful, or in practice, do you do it? Do you not need any diagrams at all?
From my experience, but again, maybe I'm from a different industry. We don't actually use those diagrams that much.
Yep.
So, but I'm not saying those are bad. I want to emphasize. It's just that I think for what we're doing, they're not that applicable. I'll say that they're certainly applicable if you're writing a higher level application, even like a cloud-based like microservices architecture, for sure. We do that actually for our cloud backend, if you want to know. So our fleet management system definitely uses it, and it's very useful. In fact, our build engineer and also our cloud engineer actually does that all the time. Yeah, so those are very applicable for sure. We have he does have an architectural diagram that has all the pipes for the RTSP stream, and then the login system, and then all the different lambdas, what they do, and all these components, for sure. But for our core compute system, it's actually a different problem. So I'm not sure if that applies directly, which is why I pointed you to the sort of like the DirectX graphics SDK framework thing. You can take a look at that one. So, but I think they're different. I think they're different problems. So you apply the right tool for the right job. Yeah.
I see. And to put it in another way, are you saying that if your components are like quite typical, that uses very typical kind of a architecture pattern that makes use of graphics stack and robotics stack that are pretty much always the same in accomplishing this kind of work. There's no real need for you to spend the time to design this using diagrams. Whereas
yeah, exactly, because it's just a different problem. You're focused on a couple of other things actually. That it's actually a different problem. I'll just put it for you that way.
Yeah. Maybe one more question, more specific question on this is whether you find those diagramming standards, modeling standards, UML useful?
I think it's definitely useful actually at a higher level. So I think, for example, at the application level, I think it's very useful. I also think it's very useful, as I said, for our backend system, which we actually do use as well, right? So
I understand that using diagrams is useful, just wondering whether, actually going to structure the diagram in a IEEE, UML, whatever standard is necessary.
I don't know. I'm not sure if you have to go that far, but maybe because we're just not that experienced in this aspect. I to be honest. Maybe it's just not us. But that's not to say that other people don't find it useful. Yeah, for sure. I'll put it for you that way.
Yeah, I mean, I guess if you need to communicate through a paper, for example, then of course you need to conform some of those standards so that the community, like academics, understand.
But in general, I'll say one thing. If you want to understand the underlying implementation of how a very complex framework works, like for ours, we prefer APIs, or at least we don't have to see your implementation, but we prefer APIs over diagrams. So in other words, I would rather see you, so let's say you wrote some framework, it doesn't matter what it is, even if it's a cloud, right? Or front end, back end, or something that is high performance like ours. I rather want to see your code. It could be just a header file, it could be your interface in Java or C# or Python. I rather want to see, I want to see that instead of seeing diagrams. Diagrams are useful, but they don't actually tell you much about the underlying implementation. If I were to see actually part of your interface code, I don't have to see your implementation, but just looking at interface, I have a much better idea as a software engineer, what's involved, what I need to call, and how, to be honest, if you're good at software engineer, you have a good idea, of course, how the data actually flows through between the components. So again, I don't need the specifics, but I prefer to look at APIs. That's my personal preference.
Yeah, I mean, I totally agree as well. One of the things that I always tell my team is that I really don't need to see, like a lot of comments in inline, but I really want to see that your interface or your basically your method signature is done properly.
Yes, exactly.
As a header, gives me a good description of how people can use this. Yeah,
absolutely, you are correct. I agree with that one, 100%.
Basically in line with this whole agile code over documentation.
Yes, absolutely, you are correct. I support that.
Yeah. So one other thing that you've mentioned just now was static analysis. So I'm just wondering whether you actually use some tool. More specifically, it relates to what we are teaching in terms of some fundamentals here as well, specifically to white box testing. That means actually doing code structural kind of analysis rather than testing for features. Some specific things that we are doing are like control flow graphs, and then using some graph methods to analyze it to see whether like we have the tests have covered enough of your branches and so on. Just wondering whether you find that aspect of software engineering useful.
I think it's very useful actually, but to answer your question about static analysis, the one we use, there's a lot of tools actually. There's Valgrind, there's Memcheck, those are on Linux, and on Windows actually Visual Studio has a very good static analysis tool that's built into Visual Studio itself, and they actually catch some very serious errors. I mean, I think I need to emphasize static analysis is actually a very important part of our entire development workflow. They catch, for example, there's actually function calls that could result in potential buffer overruns. You never wanted that to happen. And they catch those. They catch uninitialized variables. They even catch some potential race conditions in your code. And they catch things like your function not returning certain values. They actually catch a lot of very serious things. We run those, and of course Valgrind actually does it more. It's very slow though, but on Linux it will try to do somewhat the same thing, but also a runtime tool. So those things get run on the binary, and then it dumps out a report, right? And then you take a look at it. There's a lot of false positives though, so you need to be careful. But in general, it does actually fix, I would say, the big problems, right? It does fix majority of the big problems, which in my opinion is a big win. So we actually, my build engineer is actually looking at automating this process right now. So we run the static analysis headless, before the build, so that we can find out and catch these problems earlier. I'll say it's very important.
It's good, and it's good to know that, because like some of our programs, like in DigiPen, who uses C++ a lot, every piece of code that they almost every, I mean, I wouldn't say like across the board, but most of the assignments that require them to submit code, we require them to go through val grind.
They should. I would encourage that.
Satisfy a number of different
yes,
like the typical code review check.
Yeah. It will save your life. Trust me. It will save your life.
Yeah, I need to frame that statement for them. Yeah, because most students wouldn't be able to appreciate the amount of I mean, I wouldn't want to say their perspective, but it's because of the lack of experience with real world code that needs to be deployed properly, that they feel that there's a lot of these extra steps, which doesn't feel like not fulfilling, not meaningful. Looking through the memory and trying to see that everything works in a pristine condition. It's just not something that is very exciting for students to work on. I mean, yeah.
Well, I mean, that's one thing, but I can tell you this. You can tell the students, like, one day, let's say they're, I don't know, say if they're working on robot, they run the code, they build the code, and they don't do the proper checks, then the robot is 10 kilometers away from your operating center, and then it crashes, and then you realize that you actually had a buffer overrun. Then we'll see which one is more exciting. You should have done the proper checks before you made the robot leave the office. You know what I'm saying? And these things actually happen. That's when you actually have some massive regrets about trust me, it's going to save your life. Or you could go to the field 10 kilometers away and go fix it yourself. I leave it to you. I mean, it's that simple, right? You have two choices.
And sometimes we need to really feel the consequences before we will do the necessary actions.
Yeah. I mean, before you ship to customers or after you ship to customers, it's your choice, right? I'm not going to force you to do it, but if the code's going to do something terrible when it ships to customers, then you better be on the line to fix it.
Indeed. Okay, maybe one more question from me. Sure. Is that you have a long experience with DeepMotion and Pixar, which are like quite huge companies. So just wondering the differences, that you feel, or rather you do in terms of running dConstruct versus that. Maybe a bit more specific question is in terms of just now we were talking about managing the software development process. Do you think that there's something that to be learned from your experiences from Pixar, or it's like totally different ball game altogether?
Actually, it's the same. I'll say big company, small company, doesn't matter. Software engineering. I think the key is obviously you have to hire the right. So first of all, you can have all the processes you want, but if your engineers are not very good, you're still going to get really terrible code. So you see, the key is you have to hire the right people. So the level of software engineering, you have to hire smart people, and you had to hire very good software engineers. That's the first thing. Then even if they're let's say inexperienced, right? But if they're smart and they're of course hardworking, then you can teach them the proper processes and the skills to write proper code. So I think that's key to any tech company, startup or large company. I mean, that is the standard thing. So once you have those things in place, then of course you can put the proper processes. So that's at least my take on my 20 years of experience. People might have different opinions, but that's my opinion.
I think that is fantastic advice. Yeah, especially knowing that you have these deep experiences across both large and small and small but very promising companies.
Hopefully, yeah, we'll see. Yeah, we'll try our best. Yeah.
Okay, so if we go to the questions that students have asked, I thought there were a couple, but actually it's only really just a couple, two, right? Yeah. The first question was integrating technology. Have you considered integrating technologies like ArcGIS into mapping? Well, this one is basically a question on your product.
Yeah. Oh yeah, I don't. Maybe, but it doesn't. It's quite different. So there's this GIS, which is GPS. ArcGIS makes sense when you actually have the GPS coordinates of your robot, which is ironic because our system. I mean, we can definitely add GPS on a robot, no problems. But we actually made a point from day one to make sure our system runs in what we call GPS denied environments. So we want to make sure there's no GPS. Now, having said that, we can definitely put GPS in and it will work. But we want to make sure our system runs in GPS denied environments, because if you think of it like a construction site, you can go try for yourself, check. You can go, if you're curious, go to a construction site and see if you have a GPS signal. I'd be very surprised if you get one because of all the blockages, very thick concrete walls and everything. So an ArcGIS program sounds great in theory, but in practice, if you want to deploy production grade robotics in all these very harsh environments, it might not pan out. Of course, I'm not saying it will never work. If it's an open environment, sure, but it doesn't actually directly apply to what we're doing. So I guess I could go through the second question. So,
yep.
How is your development team organized? Well, I mean, we have the ML people doing the ML and vision stuff, and then we have the robotics people doing robotic stuff, right? So everyone gets together for testing, of course, because the code often interjects between different, I'll say, sections, right? So everybody, we don't point fingers, but we get everybody together for testing, and then people be like, how come your code breaks my code, that sort of thing, right? Then we all fix it together. You cannot separate hardware and software, unfortunately, for robotics. Unfortunately, it is completely just merged or tied together. That's why robotics is very difficult. There's no way you can separate hardware and software. In fact, it's always in robotics, they always say you have simulators, right? But in reality, simulators can only get you that far. I want to say again, there's no substitute for real world testing. Unfortunately, there isn't. Remember, check when we brought a robot to you, and then we had some issues as well, right? And then eventually we resolved it because of the comms and all that, right? But as I said, that is an example that in robotics, a lot of things can go wrong. It's not your software. Like what happened that day was the battery went out, or the comms wasn't there, or the SIM card wasn't functioning, right? So all these things are very annoying to fix. And again, you have to test it together. Software and hardware have to be tested together. It's very difficult to test it independently. So how much code is, sorry, go ahead. Yeah.
No, I actually have a follow-up question.
Yes.
So you mentioned how you divided the team into different technical groups.
Yes.
How about in terms of software engineering? Is there like a role like the typical Scrum Master, or whether
no, because because when I hire, and also actually in Bay Area companies, when we hire, all our engineers have to be good software engineers at the that's the basic requirements. You're a software engineer first, then you're a robotics engineer, then you're ML engineer. So you have to be able to code. You have to, and this is the same thing. Like in the Bay Area, you're a graphics engineer, but you pass the standard coding interview. Machine learning engineer, you have to be able to code. You have to be able to code in C++. You know what algorithms, data structures. You have to know that sort of thing. Because there's, I mean, I'm sorry to say this, but I think people with experience will say this. It's like a data scientist, unfortunately, is of no use to a lot of companies, for me at least, and also in the Bay Area when they hire, like we're doing real machine learning, like say NVIDIA doing self-driving cars, or you're doing some kind of a high performance like image recognition startup thing. You need to be able to write the code instead of just performing experiments. There's not much value in that, right? The real value of say even doing machine learning is not to say train a neural network. Okay, that's kind of cool, but whatever, right? Is to actually get it trained and then deployed performantly, stably, reliably, the whole process end to end, and then ship it to the customers. That's when the real value actually is, right? If you're just doing the neural network, training it, and then doing the data wrangling, I mean, that's important. Don't get me wrong, that's important work, but that doesn't result in a product, and it's just not a viable solution if you're shipping a product. So at the end of the day, all our engineers, be it ML engineers or robotics engineers or computer vision people, can all code. That's like the basic requirements. So you must have proper software engineering, which is why I think there's a lot of value in software engineering. That's actually building stuff. Then on top of that, you have your specialization. So that's why, even though they're separate, everyone, in fact, our ML engineer routinely finds bugs in the robotics. And today she's actually fixing some of the bugs in our dashpack code for the robotics guy, because she found it and she's actually refactoring it. So we don't, for software engineering, we don't draw boundaries. Everybody codes, and you got to write proper code. Yeah, clean, proper refactor code. Yeah.
I see. How about some of the stuff you mentioned in terms of like continuous
integration,
deployment, and integration? Whether there are roles. Yeah.
Oh, we have a build engineer that sets it up for us.
Oh, okay.
So we check in our code, and then they go through the CI/CD. But there's only some of it we can CI/CD, some of it, like the graphics engine part, a bit difficult. Because, well, a CI/CD is headless, but graphics is not headless. Right? You can run a head session, so it's kind of difficult. But the stuff that we can CI/CD, like localization, and then some of the dashpack data collection code, we definitely, it goes through the CI/CD process, and then we have some tests that spit out the results. Yeah, for sure.
Is this engineer one of the ML or robotics engineers, or is he a dedicated person?
That one is a dedicated build engineer.
Oh wow!
But dedicated. But he's also in charge of writing a lot. So he's more than the build guy. He also writes our cloud backend as well. Yeah.
Good.
So it's like,
that really shows how much you care about software engineering, right?
Oh, we do. We really care. So as I said, everyone in the company is a software engineer first. You software engineer first, then your specialization. But you better know how to code. Yeah, software engineer first.
Cool. All right. Next question. How much code is too much? Wow.
Well, I mean, okay, at Stanford for CS107, if you have more than 10 lines of code, the TA will deduct 2 points from you, I guess. I'm not saying that's a standard. I'm just saying you should know yourself how much code is too much. If you're writing like a really long function that's like 2 pages long, I think you should go refactor your code. Yeah. Try not to have repetition. I mean, I'm not saying over 10 lines is bad. Sometimes over 10 lines is fine, it's fine. But in general, you should try to keep your functions as terse and as short as possible. Yeah.
Yeah. Good advice. That is why there is a refactoring pattern or code smell pattern called a long method.
Yeah, exactly. Good point.
Yeah, simple name, simple thing, but
yeah, please don't make
many
long
people
functions.
commit.
Yeah. Nobody likes long functions. Other than the guy who wrote it himself, maybe. I don't know. Yeah, I'm not sure about that. Okay.
All right, next, LiDAR sensors. Receiving data from a 360 point of view.
Yes, yeah, the LiDAR sensors are, well, depends. Okay, that's a loaded question because it depends on the LiDAR sensor. Some LiDAR sensors only receive it from 180 degrees, some less, 60 degrees. Ours is close to 360, I think about 270 degrees. It really depends on your sensors. But that's not the key. The key is how you fuse the information together. The LiDAR point clouds, when they come in, are very noisy. You can't use it, just point blank, raw. You have to do your own processing, and that's where the magic happens. So that's actually where our custom IP comes in. The noisy stuff itself is not that useful, but you need it. You need it for data collection. So yeah. Cool. How do you gather the requirements required to build your features required for your first of all, we have a lot of experience building, operating and developing for robotics. Secondly, we actually work with our customers. So the scanning thing is actually what we spoke to Gammon about. So they were like, oh, we really want autonomous scanning. Now we could have built this part, check might find interesting. We could have just gone in and just hard-coded the system, a scanner, hard-coded into our system, and then just ran it. That would have worked for Gammon, but instead what we did was that we decided if Gammon wants it, there's probably a possibility that some other company, not just Gammon, might need the system for something else. So we went in and built a plugin based programmable waypoint mission system that would work with any kind of payload. So now it's very generalizable, right? And so we sort of gather from one customer and then we sort of expand on it to say, okay, what if other people want something different? Can that also fit into this framework? So we don't have to spend time, waste time, I guess, developing something completely different, right? So it's a very generalizable system. That's how we do it. Yeah.
What about how you actually gather the requirements from Garmin, for example? Yeah.
Oh, well, we go to the office and the guy like shows us his slide deck of problem statements, basically. And then he basically says, oh, I want to do this. I want to do autonomous scanning with robots because of I don't have enough manpower. Can you solve this problem? So we visited the office multiple times. And then actually when we're doing the product development, we actually brought our robots to their office and used their scanners, and we actually worked with them, because the problem is there's some very specific things. It's not just running a scanner, you know, like as Czech will know. The professionals in the field, those guys do it for their livelihood, right? Their career. There's some specific requirements on how certain things should be scanned, what the resolution should be, what the output should be. So there are some specifics that we have to adhere to their standards for construction, which is the same for any industry. So that's what we do. We after we develop the code, we go on site to the customer's office, we run it, we develop it, we test it, and then we iterate until it actually adheres to their requirements. Yeah. Basically, product lifecycle, product deliveries lifecycle. Yeah.
Sounds good. Yeah. Okay. Next.
What the work routine like? We just go in the office and work, I guess. How much time invested? Meetings. I try to keep meetings to a minimum. In fact, I've never held an actual formal meeting with my team since March. We are engineers. We hate meetings. We have informal discussions, but we hate meetings. We plan, of course. We plan on Jira. We try to keep everything online. And if you have a good enough team that's competent, competent people don't like meetings. So I try to keep all this kind of red tape, bureaucracy to a minimum, if possible. Yeah, so we try to reduce that. Yeah, more time coding, less time talking about fluff, I guess. So, yeah, I guess, yeah. But of course, if you need a meeting with customers, we still meet, so not a problem. Yeah.
We take last two questions. Yeah.
Yeah. Okay. For a company that specializes heavily on hardware software solutions, how does the team handle security of products? Yeah. So that's why the code sanitization, static analysis comes in. So the static analysis of C++, depending on the compiler, for Visual C++, Visual Studio, that is, it's actually really good. Believe it or not, in modern C++, it actually gets away with a lot of the problems previously that you had with security, like memory stomping errors. And also, there's a lot of safe functions used in C++ nowadays, like sprint_s, or the secure methods, memcopy s, and that sort of thing, that actually will address a lot of these security problems. So that's what we do. And of course, we do. Everything's encrypted. We use for encryption libraries, we use industry standards, right? SSL and that sort of thing, to make sure everything is safe. After confirming with Gammon, the SRS is also drafted. Sorry, what's SRS? I don't know what the
requirement specification.
Oh yes, okay, yes, of course,
Sorry,
of course. Yeah, of course. But actually, the SRS changes though, because they themselves. The thing is, customers often don't know what they want, so is drafted. I say in quotes. Then you go back after you have your first prototype, then they change the requirements. That happens. So you can obviously nothing changes too much, but robotics is one of those things where you have to see it to understand it and believe it. That's the way that's the reality. So it's not software. You have to experience it for yourself, because it's a piece of hardware. So you have to go in and you have to refine it a bit more. So the requirements do change a bit, but not too much. Yeah.
Okay. All right.
Yep.
I think we have reached the 11 a.m. mark. A very quick summary is that some of the key things that I think you have said that makes an impression to me, that I want to tell the students, are like no more than 10 lines of code.
Yes, please. Yeah, I support that. Please, thank you.
And then software engineering doesn't matter big or small. It is as important, even if it is small. You have
software engineers first. Yeah.
Correct. And people first, right?
People first, absolutely.
Process. Yeah. So the last thing was just what you just mentioned in terms of clients don't know what they want. So that's why you bring a prototype and show them.
You have to, yeah.
Yeah,
it's a requirement.
The requirements. All right, I think that's all the time we have.
Thank you very much.
Very thank you. Big thank you to Jiayi for spending all this time with us.
No
I know
problem.
we need to get right back to work.
Okay.
Yeah,
thank you very much. Thank you.
Thanks. So
thanks everybody. Have a good day.
Yeah.
Okay. Bye.
Bye-bye.